Alright, so for 7 through 12, we're matching the equations with the graphs. And I'm not going to go in order based on the equation. I'm going to look at the graph and then match it up, just the ones that are more obvious first. So if you look at A and your choice is 7 through 12, you just by looking at the structure of the equation, you could see that that one would be number 10. And then the logistic growth, again, that's another like different graph, right? So that would be, if you again look at your choices 7 through 12, that would be number 12 for letter F. Just based on the structure of the equation. And so now I have 2 logarithmic and 2 exponential. So B and D are the logarithmic and C and E are the exponential. So I'll start with the logarithmic. I have this one and this one. Number 9 is base 10 and number 11 is base E. So a base 10 has a sharper turn, so more like this one. A base E, remember, is 2.718, so it's a smaller number. So it's a smoother curve. But not just that, if you replace x with 0, for number 11, natural log of 1 is 0, so that would go through the origin 0, 0. This one does not go through the origin. So just with that piece of information, you know that this is number 11, and so then that would be number 9 up here. So now we're left with 7 and 8. If you look at the exponent, for 7 it's positive, and for 8 it's negative. The negative exponent is going to flip the base to 1 over e, so that would make it a decay. So this would be number 8. So that means that 7 is C. Number 13, it's asking you to figure out how much time is it going to take to double, and then how much money are you going to have after 10 years. So if it's at a rate of 4%, the initial investment doesn't really matter, because no matter what, when you double, you're going to end up with this. 2 equals e to the 0.04 t. You're solving for t. Okay, so then natural log of 2 equals 0.04 t. We're going to divide by 0.04 on both sides. And so plug this into the calculator, and you get t is 17.3. So it's going to take that much time to double the money, okay, at 4%. And then how much you're going to have after 10 years, so you're going to have A equals, so here you do want to put in the initial amount, 10,000, then e to the 0.04 for 10 years, so multiply the exponent, so you get 10,000 e to the 0.4, and then now you just plug it into the calculator. So you'll have 14,918 and 25 cents. So they tell you that it took 21 years to double. So doubling, there's little doubling. E, and so we don't know the R, but it took 21 years. Okay, so we're solving for R. So natural log of 2 equals the exponent. So we're going to divide by 21. So R is 0.033, and it goes on. So it's going to be 3.3%. So how much are you going to have, starting with 7,500, how much are you going to have in 10 years? So 7,500 here, 0.033, and it's 10. So simplify that 7,500, e to the 0.33, and then use your calculator. So you get $10,432.99. Okay, and this was the other answer right here. So on 17, you're missing the annual percent rate and the time to double. So first we have to find out the rate. Okay, we know that after 10 years you have 5,665 and 74 cents, starting with 5,000. So we divide both sides by 5,000 to isolate the E. So that's gone there. Okay, so when you divide the left side, you get 1.133148. So now you change it to log form. So natural log of 1.133148 equals the exponent. We're going to divide by 10. So the percent here is 1.2 or 1.25 if we round it to that. So 1.25%. Okay, time to double would be 2 equals e to the 0.5% t, because we're trying to find out how much time to double. And so this is natural log of 2 equals the exponent. We're going to divide by 1.125 on both sides. And so that's gone. So when you plug it in to the calculator, you get that it takes almost 55.5 years to double the money at that percent. So for 19, we need to find the initial investment, the p-value. So I already substituted the other variables. So this is going to give me 100,000 equals p. I'm going to simplify the exponent, so that gives me 0.45. So I'm going to divide both sides by that. So that cancels that here, and so that leaves p by itself. So now I just plug that into the calculator, the left side. So p is $63,762.82. You also need to figure out how much time to double. So 2 equals e to the 0.045t, because it's at 4.5%. And so natural log of 2 equals the exponent. So you divide by 0.045 on both sides. So it takes 15.4 years to double. So for 21, I went ahead and completed the table, but I changed the orientation so that it could give me space to show the work. So here you see, here's the original setup. We're tripling the money this time, that's why you see a 3 right here. And the rate is up here, and then the time. And so we're going to change it to log form, and here's the log equation. So the next step would be to divide both sides by this, by 0.02 here and here, and so that gives you 54.9 years. Oops, the right, it's not going to fit, but anyway, 54.9. And for the next one, so I went ahead and divided each natural log of 3 by the coefficient of t in each case. Okay, and this is what I got. So 27.5 years, 18.3, 13.7. Well, I could have put 11 right here, right? And then 9.2. Alright, for 23, here's a screenshot of Desmos. As you can see, the red equation, or the red graph, is the linear graph. 1 plus 0.075, this one. And the blue graph is the exponential graph. And initially, they're the same. See how the blue and the red are overlapping? But as time goes on, after about, it looks like 5 years, The blue one takes off. It's growing at a faster rate. The red one is a linear graph, so it's going to be constant rate throughout, forever. Whereas the exponential is going to be growing slowly, but it's going to be growing faster at a faster rate than the red one. Okay, so to answer the question, which grows at a greater rate? At a greater rate would be this one. Okay. Okay, so here's the problem for 25. Remember, HL is half-life. So for this isotope, the half-life is 1600 years. We started off with 10 grams, and they want to know after 1,000 years how much is left. So I can leave it like this, or just cancel out by 100, top and bottom. And so put it into a calculator, and you get approximately, so 10 times 0.5 to the 10 over 16 gives you 6.48 grams. So for 32, for 27, they're asking for the initial amount. They gave you the final amount after 1,000 years is 1.5 grams. Its half-life is 32,800 years. So again, just to put less numbers into the calculator, divide by 100. And so we're going to divide both sides, and I'll put 0.5 this time. Divide both sides by 0.5 to the 10 over 328. Okay, so that way this side it's gone, and you have A by itself. And you started off with 532 grams. So for 29, they're asking for how much you have after 1,000 years. Its half-life is 432.2. So I've already set it up. Punch this into the calculator, and you get 5.3 grams. So for 31, you want an exponential that fits those 2 points, 0, 1, and 3/10. So I've set up the first one using the point 0, 1. And so in the exponent, b times 0 is 0. So then that means that e to the 0, this part of it, this factor is 1. Okay, this is 1. So that tells me that a is 1. So now I use the other point 3/10, and I set it up 10 equals 1 times e to the b3. So now we're solving for b. So we have natural log of 10 equals 3b. Divide by 3. So that's the exact value. So you would write y equals e to the natural log of 10 divided by 3x. If you want the approximate value. Okay, so here it is. The exact equation with the exact value, and then here with the approximate value up here. Punch it into Desmos. I'm not going to do it right now, but you could check to verify that, in fact, either one of these equations go through these 2 points. So here's number 33. The points are 0, 4, and 5, 1. And so here again, this is going to give me 0. So e to the 0 is 1. So then this tells me that a is 4. I'm going to use that in the next equation. So 1 equals 4 times e to the bx. I'm going to divide by 4 first. So now I'm going to put natural log of 1/4, or if you want, 0.25 equals 5b. Divide by 5. So the exact equation would be y equals 4 e to the natural log of 0.25 over 5x. Okay, so notice when you put in the natural log of 0.25 over 5, you get a negative, and that makes sense because look at what happens here. As you go to the right from 0, 4, it went, as you go to the right to 5, this point goes down. So this is a decay. Okay, so this is the These are